So the aim of this presentation is just to give you an overview of quad boosters, their application. I do touch on briefly the fundamental principles behind how a quad booster operate, but I don't go into too much detail as they are quite complex. And I also touch briefly on the key differences between the quad booster that we've deployed and those that have been deployed elsewhere in the world. So as I mentioned, the quad booster technology itself is quite mature. It is in use around the world. And in the UK, National Grid have around 19 installations, and they've been in place, some of which have been in place since around the 1960s. However, as my colleague Gilbert mentioned earlier, we believe this is the first application on the distribution network. And whilst the technology itself and the theory is mature, the differences between the transmission network and the distribution network make it such that it's quite difficult you can't just pick it up and drop it onto the distribution network. We had to do quite a lot of there was quite adaptive works to accommodate this system. So just to start off, the quad booster itself has a number of different names depending on where you are in the world. In the UK, we refer to them as quad boosters or quadrature boosters and phase shifting transformers, whilst in America they are known as phase angle regulators. As Gilbert mentioned, they are used in parallel circuits, or they can be used in parallel circuits to control the power that flows between the two circuits. And they do this by enabling control of the voltage phase angle. And I'll go into that in a little bit more detail in the next few slides. There is also, quad boosters are also able to both increase and decrease the power that flows through the circuit on which they're connected. So there is a convention to describe that. And the terms used are boosting, which is where the power flows through the circuit on which they're connected are increased, and bucking, in which the power flows through the circuits are decreased. So just to explain that in a little bit more detail, and I apologise for the complexity of the slide, but if you look at what we have here is a parallel circuit, and what isn't shown on the graph, what isn't shown on the picture, sorry, is that the power that flows into the circuit that is generated by the generator flows out of the circuit, and that's assuming that this is a perfect scenario, and we exclude any losses on the network. So in this scenario, the only differences between the power that flows between the two circuits is based on their reactances. You can see that there's the voltage and source voltage on the source bus bar and the voltage at the receiving bus bar are the same, as is the phase angle between the sending and receiving bus bars. However, if you introduce a quad booster into the network, you're able to change the angle between the voltage phase angle between the source bar and the receiving bus bar, such that you can change this on just one of the lines. The consequence of this, given that the power that flows into the circuit is still equal to the power that flows out of the circuit, is that you have what is called a circulating power between the two circuits, and it's this what changes the relative proportion of power flows through the circuit. Now, I appreciate that was quite a mouthful, so what I've done is I've done some numbers. I've put some, actually, let me just explain. So in this scenario, you can see that the circulating power, which is shown in the circle, the power actually opposes the flow of power in the line on which the quad booster is connected, and that's the bucking effect that I described earlier. And in this picture, the power flow is actually in line with that of the power flow in the circuit it's connected, which boosts the power flows through the circuit. So I've got some numbers. Don't hold me to these, don't get your calculators out, because they are just theoretical numbers. What we have is the impedance is shown as marked as X in the two lines, and you can see the circuit on the left has significantly lower impedance than that on the right. And you can see in this scenario where there is no controllable element on the network, again, the only differences between the two are the impedances, which are at the bottom. And as such, the line with the least impedance carries the greater load, which in this case is inversely proportional to their impedances. However, if we include a quad booster into the network, as I mentioned previously, we're able to control the phase angle on just this one circuit. And in this scenario, I should mention that the quad booster has what is called a nominal position, which in theory doesn't affect the voltages on the network, and you can see that the voltage into the quad booster is the same as the voltage that comes out of the quad booster, and as such the power flows through the two parallel circuits are the same. This is a demonstration of the bucking effect. So if we were to tap the quad booster and decrease the phase angle on that one circuit, what you can see is that a circulating power is generated of 12 megawatts. This has the net effect of reducing the power that flows on the left-hand side circuit and increasing the power that flowed on the right-hand circuit. And you can see that they are much closer aligned. If you continued to tap the quad booster, up to the point where the phase angle then becomes what is termed as the optimal phase angle, the power that flows through the two circuits becomes equal. And this is what the ultimate aim of the quad booster is to achieve in our scenario, is to balance the lines proportionally. I should also mention that if you continued to tap the quad booster and further decrease the phase angle, you would eventually get to a point where the line that you're controlling is such that it carries actually less load than the other line. And obviously this isn't an optimal situation to be in. So just really to summarise what Gilbert mentioned earlier, we decided to employ a quad booster and install this on the circuit with the least impedance, which is that which connects Wissington to the Downham Market Tees section. There are some logical explanations as to why we installed it onto the circuit with the least impedance. The main one of which is the fact that the quad booster itself has a small impedance, and when you insert this onto the circuit, obviously if we were to put that onto the circuit with a higher impedance, we would further push the powers away. This one actually, by putting it on the circuit with the least impedance, we actually bring the powers inherently closer together anyway. And then just moving on, just to touch on the high-level specification for our unit and to understand how this is then different from a transmission network. You can see obviously the voltages are different, and that's by virtue of the fact that one's distribution, one's transmission. Also, you can see that the rating of our unit is significantly lower at 30 MVA than what you would have on a transmission network. And consequently the unit needs to be smaller to fit into the locations that we have them installed. So to achieve this, what we had is a dual-core system, which is similar to what is on the transmission network, but it differs in the fact that both cores are installed in a single tank, whereas on a transmission network, generally they're installed in two tanks. And the final point to note really is that due to the nature of the distribution network, we wanted the control system had to be automatic to enable us to control the system and to not only control it, but so that it can react to changes in the network. Typically, at transmission network, they're controlled manually. I should also stress here that these are just the high-level differences between our quad booster and those that are installed on the transmission network. We do obviously touch on the more detailed differences later on in the afternoon session. And finally, to recap on what Gilbert was explaining earlier, what we have here is two graphs. Both graphs show a plot of the circuit loadings against the Wissington generation export. The orange line is the Downham circuit, the purple line is the Norfolk circuit, and the blue line is the Sudbury circuit. What we have at the top is what we have now currently, and these results are generated from our network model. What we have now is the Downham Market circuit reaching its capacity of 30 MVA at around 54 megawatts export. Whereas what we have at the bottom graph is the impact of the quad booster in its optimal position, at which point you can see the Downham Market circuit and the Norfolk circuit are very much balanced, and we have significantly more export capacity in the system. They don't actually reach their capacity at the full 70 megawatts of export. Although I will stress, obviously, that this is where we are, and these are the models, the results. Over the course of the year that we're trialling this solution, we will take a lot more detail to understand, firstly, if this is the actual results, to confirm that these are the results that we actually get from the quad booster, and secondly, to understand if the modelling is, to confirm that the modelling of the unit is actually correct. And as I mentioned, obviously, the initial aim of this was to generate additional capacity, and by virtue of these results, it would appear that we can achieve that. And then just to recap on why we chose a quad booster and our expectations for it. Obviously, it increases or makes our network what is called smarter, which is a bit of a buzzword, but it enables us to make better utilisation of our existing assets, which makes sense because to install more copper in the ground costs a lot of money. The initial economics for the system were much better than those for the traditional systems. The figures here, which don't quote me on precisely, but they're around 1.6, 1.7 million to install this quad booster, and obviously you heard from Gilbert that the other solutions cost around 3 to 6 million. It obviously gives us much more control of the network, which enables us to confidently put this in a distribution network that does change quite frequently. And obviously the intrinsic benefits from the project are that it is the first, as far as we're aware, it's the first quad booster that's installed on a distribution network. And obviously by being the first to deploy that, we learn most from the mistakes, obviously, that you make along the way, and obviously everything that you capture along the way. There are obviously some implications. It was very complex. It needed to be installed into a live network where there was some real faults. Not real faults, sorry. Where there's some real... It obviously couldn't affect the operation of the system, the current system. Obviously, British Sugar are quite a big customer for us, and we didn't want to impact on them in any way. And it stretches our existing protection coordination capabilities, and that's explained in more detail in the later session. Obviously, these were our expectations. It's been installed since around July, August last year. So we do have some initial results. Yep, we have some initial results. So what we have here is some average data that we have collected from site. So the graph is a similar graph to what we just had. What we have on the left is the circuit loadings for the 3 circuits, and at the bottom we have the export for each of these the exports. The solid lines are based on actual measured data from site, whilst the dotted lines are what we've projected based on those measurements. Unfortunately, due to the loadings on the network, the quad booster control system the quad booster hasn't needed to tap to increase its tap and bring them closer together. So it's actually just been sitting on nominal tap for quite a few months. But what you can see, even from it being on nominal tap, the lines are actually inherently balanced. As I mentioned earlier, the impedance this introduced by the quad booster makes them closer aligned, and it would appear that the increases in export capacity of around 10 megawatts might be realised. The only significant point to note here so the lines that we have for the Norfolk and the Downham market are very similar to those we modelled. The only significant difference is that the Sovereign circuit appears to carry more load than what it does when we model the network. And over the course of the next year, we'll be re-evaluating our network model to understand why that's the case, to understand further why that's the case. And obviously, as I mentioned, we'll also be undertaking further trials to confirm the impact of the quad booster in its optimal position, so as to confirm what actual additional capacity can be made available for customer connections. So the final point to note is that the quad booster, whilst I mentioned it hasn't tapped many times, it has actually tapped. So we can confirm that the quad booster has been sent and received signals from the control system and is operated in accordance with the control system design. There's been no maloperation of the protection system. It's remained stable since it was put in operation. So everything appears from this first view of the results to be on track. Thank you very much.